Hello everyone. Good afternoon from here in Abu Dhabi. I hope that you can hear me clearly. If you're able to hear me, just let me know by typing in yes in the chat window. Oh, perfect. I am receiving quite a lot of replies. Great. So using this chat window, please feel free to introduce yourself, your position, your company, and the country you belong to. So it's really great to see an international audience of people from all the industries and backgrounds joining in our webinars. Okay, great. Thank you everyone for confirming. I welcome you all to today's webinar, which is the fundamental of performing SIL studies as specified in IEC 61508, IEC 61511, and ISA TR 8400002 using VAIL-PHA SIL. I am sure that you are able to see the slides clearly as well. So my name is Sayyida Samia Aves, and I am the lead software engineer at Velosi. For the next 2 hours, it will be our pleasure to host this webinar for you. We would like to thank you all for joining in today, and we hope that by the end of this webinar, you will have gained good knowledge about the subject matter. As some of you may know, that this is our 57th webinar in a series of technical webinars. As a practice, we are conducting one webinar every second Sunday. So you can follow us on LinkedIn and make sure to check out our website to stay tuned to the latest updates. Also, we are uploading our webinars on our YouTube channel, which is Velosi. So please feel free to subscribe to our YouTube channel in order to stay tuned. So today we have quite an experienced panel of speakers. I'm here with my colleagues, Mr. Ijazul Karim Rao, Managing Director, Principal Integrity and Safety Consultant, Mr. Anthony James Williams, who is the General Manager of Global Sales, Mr. Farasatullah, Process Safety Engineer. So I can assure you that you all are in great hands today. During this webinar, we encourage you to keep asking in questions in order to clarify any kind of doubts that may arise from time to time. This will not only help you, but also the others who may have similar kind of questions and similar kind of doubts. You can type in your query using the Q&A window, and either we'll reply you live in the session, or we'll type in the answer for you in order to clarify that question. We'll try to answer as many questions as possible during this session. Furthermore, we'll have a detailed Q&A session by the end of this webinar. So please accept our apologies if your question is not addressed. We usually receive very high volume of questions, so we need to be very selective. We'll also be issuing a participation certificate to all those who have attended at least 80% of the webinar and have participated in the discussions through Q&A. So the agenda for today, since it's quite a technical subject today, and we'll be touching the key theoretical and practical aspects of fundamentals of performing SIL studies as specified in IEC 61508, IEC 61511, and ISA TR 8400002 using VAIL-PHA SIL. So agenda is we'll be starting with the Velosi introduction. We'll be going through why SIL is important, what is SIL and SIL determination techniques, test interval calculation and SIL verification, development of safety requirement specification and STR calculation, MTBF, MTTR, and VAIL-PHA, the reports using SIL software, and the Q&A session. So this webinar will be inclusive of a practical case study, which we had conducted for a client. So please note that the client name and the data have been redacted. We'll be following a practical approach where we'll walk you through the key steps through this case study. So before we begin with our agenda for today, although most of us are in the comfort of our home, we should be aware of the emergency exit. Due to the current COVID-19 situation and its emerging variants, we should be more careful, keep a safe distance, and in general, take care of ourselves and of those around us. So now I'll hand it over to Mr. Ijazul Karim Rao, who will begin with today's session. Thank you, everyone.
Assalamu alaikum and good day, everyone. I know this we are conducting this session from Middle East, but it is being attended by the participants from Far East, Europe, America, so there are different time zones. It's a very interesting topic, and both myself and Mr. Farasatullah Khan will be conducting it. The main part of the session will be conducted by him, and induction part and theoretical part would be covered by me. She is a well-experienced process safety engineer, and I'm certain it would be beneficial for all of you. So why SIL is important, right? And this is like the concept point of view, or like these incidents which occurred 1975 or afterwards, Piper Alpha, which caused many fatalities or the loss of property as well. So this one is a Felix Foro disaster in 1975, where cyclohexane caused the disaster, and 28 people were killed. So there's a second one, basically 1976, dioxin release 6 kilometer into 1 kilometer circle, and 17,000 people were affected. 2,000 people were treated for poisoning, and 600 were evacuated. Now, how we can basically prevent such kind of incident which occurred and which may occur at your own facilities as well. So practically there are various layers of protections and mitigations which if we focus, and we normally basically plants are built with the same concept. And like the first thing is process, or the chemical process which would be occurring within the chemical plant or process plant or hydrocarbon plant. Then which is called prevention system, where all the hydrocarbons or combustible toxic material should remain within the pipes and pressure vessels, and it should not be exposed to the environment. Second, there are basic process control systems which are used to operate the plant, like temperature control, process control, flow control, pressure control, level control, vibration control, and so on. So third thing is like there are basically alarms and basically trips which are provided on the plant, which are attended by the operators. And if any where there's high level, there would be alarm, and operator can intervene. If there's a high pressure alarm, then operator can listen that alarm and can intervene and control the parameters which are causing that high level and high pressure. Similarly, there are instrumented safety systems or safety instruments or SIPs which can trip the plant if abnormality goes more than the basically alarm, or if operator is unable to take any protective system. Then there are basically, in case of pressure, there are PSVs. For example, if alarm is not attended and then SIF is not acting, then at least pressure safety valve should be able to pop up and fluid should be able to go out. And similarly, in the tank farm areas, to control the leakage of a tank within the specified area, bunds tank dikes are made, and that is one of the area where how you can prevent the extra spread of the major hydrocarbon or a chemical which is stored inside the big tank. Then in the plant area, facilities or buildings, fire and gas detection systems are installed, which again detect in case of any leakage or any initiation of any fire, so as the corrective action can be taken on time. Then the mostly and the last basically important action is emergency response plan. If something goes out of control, then there should be escape routes, there should be evacuation process, and there's also involvement of the community with reference to civil defense, firefighting systems, hospitals, or district management of that particular area. So if you see this, there are about 9 areas, 9 considerations which are placed to ensure that if the plants are built in any particular area, those are operated by within the safe limits, and there are particular actions taken to prevent whatever anything which may go wrong. Now, definition point of view, there's a big like a terminology what we normally use in the SIL. I know that like in 2 hours time, we'll not be able to train you for the full SIL process, but you would be able to have a fair idea what is SIL and how SIL assessment is done. So that is basically a focus. So BPCS is the basic process control systems. Normally we call instrumentation and control system of the plant. Then cause an event, situation, or a condition which result or could result directly or indirectly in an accident or incident. Consequence means if something goes wrong, what would be the effects on the people, on the asset, on the surroundings, on the production, on the basically reputation of the company. So consequence mean the effects of the failure. Final element, one is basically definition of SIF. In the SIF, there are three components: initiator, logic solver, and final element. Final element is the action of the equipment which will prevent the incident. For example, ESD valve or closing of the motor or turbine so as the production could be stopped. Hazard, potential to cause harm, including ill health, injury, damage to property and products or the environment, production losses or increased liabilities. Potential to cause harm. Hazard means any abnormality basically. Initiating event, a device failure, like normally there is sometimes there's an example of butterfly effect or any cause which initiate the process. Any abnormality in the system which initiate the abnormal process. And there is a saying, for example, there is a one butterfly in the Amazon jungle, and there's a drop of water on that basically butterfly, and that may cause some kind of effects on the local environment, that local environmental impact goes on to a global, and that may have impact other basically we'll say country or region. So that's called the initiating event, the event which can be initiated by any particular process. In process plants, so there could be like a high temperature, high pressure, high flow, high vibration, or anything kind of like uncontrolled reaction that could be an initiating event. IEF is basically initiating event frequency, it's called, like initiating event frequency. Now, which is basically how, what is the possibility that event may take place, and what is the feature fast track with the help of which we can identify what could be the frequency or at what rate this abnormality or hazard or deviation may take place. IPL is independent protection layer. These are basically the various protective layers what you normally build. Generally, we have a saying like there are 5 protection layers, which is called protection, detection, control, mitigation, and emergency response plan. And nowadays, in ADNOC, there are now 7, structural integrity and life-saving, 2 more protective layers are added. Whereas in a process plant point of view, there could be alarm, there could be PSV, and there could be a SIF. These are the 3 independent protective layers which may act during any abnormality in case of high pressure. Logic solver mean basically the controllers, and in process plants normally PLC, DCS, SCADA system or ESD system, they are called normally logic solvers. LOPA is a layer of protection analysis which we normally use for the SIL analysis. This is one of the technique of SIL analysis. And SIL means safety integrity level. I will be covering this next part. PFD is probability of failure on demand. Like what is the potential of any SIF or any PSV or any protective layer which may fail in case of demand. RRF is risk reduction factor, which is normally 1/PFD. Safeguards, the physical or procedural measures in place to reduce the likelihood is normally called safeguard. Sensor is basically initiator or transmitters, part of the BPCS or SIS that measures or detect the process condition. Severity is a measure of the degree of impact, like basically severity also called consequence, like what could be the impact on the environment, on the safety, on the asset, that is called normally severity. SIF is a safety instrumented function, is also called SIF, or sometimes we call it SIS, safety integrity system, with a specific integrity level that is necessary to achieve functional safety by putting a process to a safe state. or maintaining it in a safe state under predefined conditions. SIFs are instrumented using safety instrument systems. So I covered SIS also, safety instrument system, which is part of, we can call sometime as a SIF or SIS. Those are correlated, and ESD system, a complete, can be called as a SIS. TMEL is basically target mitigated event likelihood. This is a difficult to basically have idea at this stage. So my colleague will cover it when he will be giving you the introduction of LOPA. It would be used there. Target mitigated event likelihood. This is a little difficult definition to explain at this stage. Now, what is SIL? SIL stands for Safety Integrity Level. Safety integrity level is defined as a level of risk reduction provided by safety function. It's a way to measure the performance of a safety instrumented function. A SIF is combination of basically sensor, logic solver, and final elements that detect the hazard and bring the process to a safe state. Like these are the transmitters. Then you got logic solver is DCS or ESD system or PLC, and the final element could be like a ESD valve or shutdown of the motor or a turbine. SIL of a SIF define the reliability range. And for example, when we say SIL 1, it means that a probability of failure of that particular SIF is 1 out of 10 to 1 out of 100. Like RRF, risk reduction factor, is 10 to basically 100, or the system is reliable from 90 to 99%, whereas SIL 2, 99 to 99.90, 3 mean 99.9 to 99.99, and 4 mean greater than 99%. And similarly, it means 1 out of 10, 1 out of 100, 1 out of 1,000, and 1 out of 10,000. So this is a normal definition of SIL in accordance with IEC 61511 standard. For example, if you have a high pressure shutdown with a probability of failure on demand, which is called like RF, basically 100, or PFD is 0.1. So it will come under SIL level 2. So SIF example point of view, like this is the relief valve or ESD valve, I would say. And there is a logic solver. So in case, and there's a transmitter, there's a logic solver. PT is covering high pressure, then message goes to logic solver or the ESD system, and they will either open the valve or close the valve, depending upon the situation, whatever the function is given. In the final elements are covered normally ESD valve, which normally close on demand, and others are BDVs, blow down valve, which open on it. Other little more complicated example where we can differentiate between SIF and also BPCS. Here, this part level LT101 LIC, and this is the throttling valve, control valve. This part is normally called basic process control system, BPCS. Along with the same, if there is a other transmitter, independent transmitter, and this is giving signal to the logic solver, which is ESD, and that will be closing or opening this ESD valve as a final element. So this is the another example, what is called SIF. Now, another example, like we normally call voting system, and this would be coming in the next generation when you will be doing a SIL verification. Here, for example, there are 3 transmitters, and these 3 transmitters are giving signal to this logic solver, and this logic solver, if get the confirmation from 2 out of 3, if the incident is confirmed or situation is confirmed by 2 transmitter out of 3, then it will give signal to logic solver. Logic solver will give signal to the final element to take their action, close or open. This is called like another example how the SIF complication or the more reliability is increased. This could be a HIP system, which normally carries 3 transmitters minimum. This is another video which is showing that how the BPCS and SIF systems are basically differentiated. Now here, this is the BPCS And then another one is a SIS, which taking care of the level alarm high and level alarm high. At level alarm high, BPCS is taking care, whereas when level alarm is high, one level further and BPCS could not protect the system, then SIS or SIM will take care the system. This is a normal operation. In case of degraded operation, means when there's abnormality or power failure, in that scenario also there would be override by the SIF or SIS. So a few questions I've tried to ask, like just to make sure we remember what we discussed up to now. I know that it's a little difficult subject. I would suggest not to get worried, just go by the flow and you will get some idea. And next time when you will do this exercise yourself, it will give you more confidence. So it's not so difficult to follow the SIL methodology and to carry out LOPA or any risk graph or risk matrix approach and SIL verification further. But we need to follow the system, and there should be some coach or mentor who can guide you, and then it can be easily done. Is the role of mitigating type SIF to prevent a hazard? B, reduce escalation. So there could be like a first thing is reduce escalation, but sometimes SIF can also prevent a hazard as well. How many subsystems make up a SIF? I discussed earlier also. There are three elements minimum: initiator, logic solver, and final element. The name basic subsystem of a SIF. Okay, the same question. So first three system and then the name which I gave you, the like initiator, logic solver, and final element. What is the PFD range for SIL level 1 function? PFD is first probability of demand, probability of failure on demand. It should be PDF. It should not be PFD. There's a typo error. It should be PFD. Probability of failure on demand for SIL 1. It, as we said earlier, it is 1 out of 10 to 1 out of 100, 0.1 to 0.01. What is the risk reduction factor expression? As I said, 1 out of 100, that is a RRF. PFD 0.01, then RRF would be 1 out of 100. So same questions are there. The expression for RRF is 1 over PFD. See, this is a little practical approach to understand. Like SIL is normally carried out, SIL study just after HAZOF. The first thing is like there should be HAZOF study done first, and then you can go to SIL. Or you can do also SIL without HAZOF, but it will require a little more work on the SIL team, and there would be more guesswork rather than actual determination of hazard. There are basically severity and there will be probabilities, and which normally we use under the SIL determination stage. My colleague will be covering in the next example. So main objective at EPC stage is like to determine, like first of all, to establish what new SIFs or control system we need to install. Like if we are doing any deviation or hazard analysis, then it will guide us like what protective layers we need to add. If a LOPA we try to conduct on any severity 4 and above or high severity, we can check that how many layer of protections are required and what would be the risk reduction factor for each IPL, and then accordingly their factor can be considered. And secondly, at EPC stage, we establish the basis what should be the reliability level of a hardware which would be installed as a part of the SIF or as a part of BPCS. So SIL determination normally at EPC stage target the selection of reliability level for the hardware which would be purchased. Whereas at operational stage, the objective of SIL determination is mainly focusing to determine what should be the testing interval of the SIFs. Like at what stage we should test each SIF, whether shutdown to shutdown, within shutdowns, after 2 shutdowns. So as like we are not testing everything every day, or we are not forgetting testing of the SIFs forever. So that is the purpose of the SIL for the instrumented functions or controls or SIFs. Now, here are certain like good engineering practice, or if I say Norwegian industry, have established, and nowadays in the new ADNOC standard, they also have established minimum SIL levels when you are buying any new hardware. Like we have seen, if I try to share my own experience in this regard, when you are doing HAZOP and SIL studies for the EPC contracts, normally EPC teams are trying to reduce the severity, and if they say there would be no fatality or there would not be any impact on the assets in case of any hazard occurs, so in that scenario, a severity level would be low, and accordingly SIL level would be low. And then if you are buying any hardware or any instrumented function equipment, then you may not be required that high reliable equipment. It means the equipment could be bought from any supplier. It should be bought from a good reliable supplier with having proper track record. So to cover that risk, the companies have now established, for example, any instrument used under PS, like pressure switch high or level switch high, it should meet minimum SIL 1 criteria. For level switch high and knockout drum, it should meet minimum SIL 2 criteria. Temperature switch high or temperature switch low, minimum 1. Whereas pressure switch low, leak detection, it could be 0. So these are the like minimum, there is a logic, right? So as EPC are not providing low reliability equipment based on the SIL classification done during the project. And there could be other drivers as well. If like a team is weak and if somebody can convince we don't need a reliable equipment, lesser SIL is applicable. So in that scenario, you will end up buying basically less reliable equipment. Similarly, under operational phase SIL as well, SIL assessment exercise as well, we have seen where when a client SIL team is sitting and they're making the analysis, they may say there's no fatality would occur, nobody would get injured, or there would be no damage to the plant more than $1 million or $2 million, and so on. So in that way, the SIL, every SIF will come under SIL 0 or SIL 1, like lesser SIL classification zones. So in that scenario, if SIL is lesser, the interval would be longer. So it means at operational phase as well, even the operational teams or instrumentation control teams working from the client side or operator side may try to reduce the SIL targets, and in that scenario, they will end up reducing their workload. So there is a conflict of interest in both sides. EPC, if they will be providing SIFs with lesser SIL targets, they have to spend less money. And similarly, at the plant level, if they would be determining the SIL targets at the lower side, they would be doing less work on the functional testing. So to make a balance, ADNOC has also identified minimum SIL levels for the type of SIFs. And similarly, in the Norwegian oil and gas industry also identified minimum SIL levels, which should not be reduced by the analysis process, even though you can have both a minimum SIL level determined by the SIL study process and then a target given by the standard. So these standards like IEC 61508, IEC 61511, and ISA TR 8400, these standards does not specify minimum SIL level. However, there are the standards which are prescribed or adopted by the operators. They describe like a minimum SIL level should be this one. So like safety life cycle point of view, these like three standards, if we go back a little bit. See, 61508, functional safety of electrical and electronic programmable electronic safety related systems. This is general requirement part one, the various parts are there. Similarly, this is the safety instrument system for the process industry sector. Framework definition, this is part one, various parts are there. And similarly, there is a safety instrument function SIF, safety individual level, evaluation technique part one. This is coming from the ISA standard. So when we say a safety life cycle, means there are various stages. Like first thing is the conceptual stage, then feed stage, feed design, and then we try to establish the requirement of the SIF, and then specification of the SIF is prepared, and then we go for EPC stage. At EPC stage, we are also buying the SIF from the suppliers or manufacturers. So then manufacturing process comes in, then SAT, FAT, Factory Acceptance Test of the SIF, and then the SIFs or ESD system or a complete PLC system or DCS systems are installed along with ESD system, independent one, or fire and gas detection system, and then installation in the field, then field acceptance, testing, and then putting the SIFs in operation. And then during operation, we need to carry out functional testings at intervals, and then we need to make analysis and make sure the SIFs are operating within the acceptable levels. Discover the complete life cycle from the initial design stage to the final decommissioning stage. Like a phase one, like the various phases are there. Phase one is definition stage or conceptual stage. Like then once the necessaries, these are the processes. If we go like a normal process point of view or book knowledge point of view, then I have to go through these steps. Like a phase one, define the scope in terms of physical, social, and political boundaries, and addresses the safety implication in terms of hazards and the perception of the risk, which should be managed by this SIF. Now, phase two, once the necessary risk reduction has been determined, the means of achieving it are specified during the allocation, phase two, and overall safety requirement in phase three. Phase four is the overall safety requirement are engineered as a safety function, optimization of functions, separation, and other design issues such as testing philosophy are examined at the point, and the planning for these activities is addressed in phase like 11. And then phase 5 to 10 demonstrate that the standard is not restricted to the development of the system. Like if you, these are the book point of view. However, if I see as a normal engineer, I go for concept and feed, that at EPC stage, we procure them, install them, commission them, and then we go to operation phase, we use, we operate, and we test them. So in this way, and last is the commissioning stage. So this way, these all steps are covered in 11 steps, but they are in writing point of view, they're a little bit complicated. But in normal life, it's very easy to follow life cycle of management of the SIPs. Like next is like when SIL studies can be done basically by Excel spreadsheet as well. I've been doing so, and then we develop software we called VAIL-PHA. VAIL-SIL is part of VAIL-PHA, and the question is why we are using basically software instead of using spreadsheet. Like even though simulation or hazard analysis can also be done by an Excel spreadsheet, however, there could be a lot of data which should be recorded, to be collected, collated, and arranged to conduct the SIL studies. My colleague will show you the software, and you will understand that why it's necessary. As we need to have the SIF-related information in a loop-wise or easily arranged manner, which could be correlated with HAZOP recommendation, as well as the software can manage this easily. If we need to perform SIL determination by using 3 methodologies like risk matrix, risk graph, and LOPA, all 3 studies can be compared, and we can see the comparison or results of these 3 studies anytime. If we need to calculate the functional testing interval as require the probability of failure data, so in the software you can have or build up a directory for the failure rate data of the various components of the SIL. If we need to perform SIL verification, where we can correlate actual testing intervals and the failure rates of the operating plant or facility, it can easily manage through the software. If we need to perform a spurious strip rate calculations, it can also be managed easily. And similarly, if we need to have any kind of report, we can prepare reports and we can extract the reports as it would be required. So now I would be handing over to my colleague. So, okay, we'll take questions also. My colleague, Mr. Farasadullah Khan, would be Mr. Farasadullah Khan of SHA, would be taking care. So he's one of our brilliant engineer. His presentation skill is a lot better than me. He has done a lot more work than me as a working engineer. and he will be presenting in more details. And there are a few questions I will take at this stage. Then I will hand over platform to Mr. Fasulullah Khan.
One question here. In a very easy approach, what is SIL2 requirement?
SIL2 requirement means like when we are buying an equipment, its reliability should be such. If we test that equipment 100 times, it should fail only one time. Secondly, if we test 100 equipment of that same group, only one should fail. So it's a 1 out of 100 failure rate. That means the SIL level 2.
There's one question here. For the same question, an easy approach, how can you explain SIL 0?
SIL 0 means it does not require any specific like reliability level, right? So if we test equipment, if it fail or pass, it does not matter. That is a SIL 0 mean. Reliability expectations are not so many. So over to Mr. Fasulullah Khan. Thank you, everyone. I will be coming back at the end with the question answer session when Mr. Fasulullah Khan would have completed his part. Thank you.
Thank you, Mr. Ejaz. So theoretical part we have completed. Now we will go through the software part, in which we will discuss each tab of the software, which is a VAIL-PHA SIL. So SIL determination requires care. Thus, one should also take care when choosing the SIL assessment software or the SIL calculation software. So this VAIL-PHA is a powerful yet easy to use Velosi's proprietary leading process hazard analysis software. It has different modules. We can perform or we can conduct HAZOP, we can conduct what if analysis, FMEA, RCA, as well as SIL safety integrity level. It is specially built to execute all stages of SIL classification. We can do SIL classification by 3 methods. We can choose risk matrix, risk graph, layer of protection analysis method. We can also perform SIL verification. We can also calculate the testing intervals, and then we can also prepare the safety requirement specifications, and we can also calculate the spurious drift rates as well. So it also supports the test intervals and STR calculation of safety instrumented functions, and it is developed in compliance with ISA TR 8400.02, IEC 615011, and IEC 61508. So before going to the application of these risk assessment techniques, I will show you a little bit about the software, that how we can manage the software. For example, this is a personal tab. We can put the company's information in it, and then the personal information. This is a default view when we open the SIL module in the software. And then we can also add the summary. We can add the description and the person who is conducting the SIL study and all the team members as well. Then in the sessions, we can add how many people attended the session, like an attendance sheet. And we can add a new sessions as well. For example, firstly, it was 3-day session, and the same team was arrived with the other session. We can add the session 2 details as well. And we can mark the attendance of the participants. Then we can add a new SIF in the software by adding a SIF details. There is a hierarchy. For example, the area, and then plant, and then what unit of that plant, and then for example, if there is a reactor, there is a compressor, there are SIFs which are related to compressor, SIFs related to the pumps, all can be grouped in a certain hierarchy. And then in the SIF data, before going to the SIF data, let me explain it in detail. We can edit this information regarding the particular SIF. For example, what is the parameter? What is the equipment tag number in which that SIF is installed? What is the SIF tag number? We can search that SIF tag number into the search bar as well. And then what will be the worst consequence if the SIF fails? And what is the study basics which we are following? And what is the PNID number in which that SIF is marked or present? What is the plant number? What is the area? What is the loop type? For example, this is a high pressure, and what is the unit number? So all this information, it will be common if we are using this graph, this matrix, or LOPA. So this information is common for all these 3 methods. So when we click this SIF data, this SIF data, we can put more details about the SIF. For example, SIF description, initiator, its detail, logic solver, its detail, and the number of final elements what we have, and then SIF description or SIF narrative and associated ESD and all the associated documents like what standard we are using, what are the guidelines we are following, and then HAZO preferences, PFD, PNIDs, and then any other diagram like logic diagrams or cause and effect diagrams, their references, and then this other detail as well. And then in this software, we can assess or classify or determine the SIL levels by using 3 methods: risk matrices, which are qualitative methods, risk graphs, which are qualitative methods as well, and then layers of protection analysis method, which is a semi-quantitative method. So in risk matrix, we have to choose only 2 parameters: the consequence severities and the likelihood or probability. We will have the risk level. It is a relatively simple method than the other 2 methods. So we will go in detail as well. So SIL determination using risk matrix. So VAIL-SIL contains risk matrix for 3 kinds of risk. It can be with respect to safety. It can be with respect to environment. It can be with respect to commercial and reputation as well. So this is dynamic. We can add and we can select the risk matrix. We can edit the risk matrix as well as per the company risk matrix. So user can specify the severity level and probability. System will calculate the risk level and SIL level according to the matrix. So whatever matrix they are using, it can be added here in the master data, and then accordingly, but choosing the risk matrix or probabilities. Now the question is where the severity level or probability will come. So it can be determined with the help of HAZO. So by taking the input from HAZO, we can take the severity levels or the likelihoods from HAZO study, and then we can put it here. We will get our required SIL level. Similarly, SIL determination by using risk graphs. So there are certain parameters in which we have to choose in between. For example, in risk graph, there are only 2 parameters: probability and consequence severity. So in risk graph, there are normally 4 parameters: demand rate, consequence, occupancy, probability of avoiding the hazard as well. So it is relatively quick method as compared to LOPA, layer of protection analysis. It is relatively quick. It tend to be conservative. They can be qualitative or semi-quantitative, and it works better if semi-quantitative. How it can be semi-quantitative? If we specify some ranges, like in case of demand rate in terms of years, 1 to 10 years, or less than 1 year, or less than 30 years, like this. So the risk, so SIL determination by using the risk graph, the process begins by defining the equipment under control and the environment in which it operating in the following sequence. First of all, we have to identify the boundaries. Then we have to identify the hazards associated with that equipment under control. And then for each hazard, we have to assess its likelihood and consequence of occurrence without any protective system. And then, knowing the frequency and consequence of all hazards, we have to determine the current risk levels, and then we have to determine whether the current risk levels are acceptable or no. And then, if the risk levels are not acceptable, then we have to consider the risk reduction to be achieved by external risk reduction factors. For example, we have to add certain layers. If an electronic, programmable electronic system based SRS is required, then utilize an approach such as risk graph to determine the requirement of the SIL level for the proposed system. If a SIL level is required, then determine if the design of a proposed safety system meets the numerical requirement of probability of failure on demand for the SIL level specified. It will be clear when we will go into the example. And then in the end, we have to ensure the compliance with the remaining requirements of the standard for the particular SIL level chosen in terms of documentation requirements and software architecture and testing. Similarly, like this graph, it is also with respect to safety, environmental application, and commercial consequences as well. Because sometimes in the company's risk matrix, the risk matrix is different for the values are different for the safety point of view or environmental point of view or commercial point of view. So we can determine for each separately as well. So first of all, let us suppose we are determining the SIL level for the safety point of view. So the starting point is this, and we have to first of all select the C parameter. What the C parameter is the consequence or the extent of damage. So this is the first parameter in this graph which we have to choose. So there are 1, 2, 3, 4 parameters we have to choose, and then in the end we will get any SIL level based on these parameters. For example, we are choosing CB. CB is the as per the risk matrix. This is a sample risk matrix. This can be changed with respect to company. Severe irreversible injury to one or more persons or death of a person. We are choosing CB. Then the next parameter is frequency and exposure time. So in standards, I will also explain in the next slide that what is the meaning of CB as per the IEC 61511-508. What is the meaning of FA, FB? So let's suppose in simple terms, FA means seldom to relevant frequent or frequent to continuous. So let's suppose after CB, we are selecting FB. And then the third parameter is hazard avoidance or mitigation. For example, there are enough number of protections and it can be hazard can be avoided or mitigated. For example, PA means possible under certain conditions to avoid the hazard, and then PB mean hardly possible. So we have selected CB, then FB. Let us suppose we have selected PA, that there are enough number of protections we have, and it is possible under certain conditions to avoid the hazard. So now we are here. So the fourth parameter which we have to select is the demand rate. For example, the consequence, the frequency of the consequence or the probability of the occurrence is very high, relatively high, or low. Let us suppose it is very low, then we can say that no special requirement. And if we say it is low, then it is coming as SIL 1. And then if we are saying that the occurrence probability is relatively high, then it will be SIL 2. So this type of determination depends upon the team which are determining the SIL level, the team members as well, that what the for that consequence, what type of severities they are considering and what type of probabilities they are considering while assessing this one. So this is for the safety. Similarly for the environmental and commercial as well. So before going to that, I will let me explain these terminologies. For example, this is a screenshot of the standard CA, CB, CC, CD. These are the classifications. For example, minor injury or the statistical number of the fatalities. So based on these parameters, companies can define their risk matrices as well. And then, for example, this FA or FP, this is a rare exposure in the hazardous zone. Occupancy is less than 0.02. And then FB is frequent to permanent exposure in the hazardous zone. Occupancy more than 0.02. And these are the descriptions that exposure probability in the hazardous zone. Occupancy is calculated by determining the number of hours the area is occupied by the most exposed individual and dividing by 8760. So this is the number of hours. So basically, how many hours operator is present in that area in a 12-hour shift. For example, if he is available 2 hours or 6 hours in a 12-hour shift, so probability or the exposure factor will be 6/12. If it is if he is available 2 hours in that area in 12-hour shift, so 2/12 will be the exposure probability. So if it is less than 0.2, it will be FA. We will select FA. If it will be more than 0.02, we will select FB from this graph. And PAPB means possible under certain conditions. And credit claim for risk reduction should be limited to the factor of 10. And then almost it means that each layer is providing risk reduction of at least factor 10, means PFD of 0.1. and PB means almost impossible, no reduction in the risk. And then similar W1, W2, and W3, demand rate less than 0.02 per year, demand rate from 0.2 to less than 0.2 per year. So this is the frequencies. This is the sample from the standard. It can be adjusted with the company's risk metrics. So we can perform self-determination in our VAIL-PHA for safety graph. It can also be adjusted with the help with company's risk metrics in master data that CSCB, what CA means, we can add it here. For example, CC is important or exposure. We can change these parameters in the master data. We can update it as per the company's risk metrics. We can perform the SIL determination by using risk graph for environmental and for commercial as well. And in this software, we can also maintain the data of the HAZOP as well. That what are the causes, what is the design intent, what is the consequences, what are the safeguards we have. So we can store that data in failure consequence analysis as well. Also, it can be imported from HAZOP module as well. And then risk graph methodology for the environmental. So this graph is similar to that one, except for the commercial. Let me go to the commercial. The description is relatively, it will depend on the environmental now, that what will be the CA means, a release with minor damage that is not very severe, but is large enough to be reported to facility management. And if you are selecting CB, for example, there is a LOPC case, an event resulting in local outrage, local or brand damage because of that loss of pressure containment, and then CC and CD. So these are the descriptions of these parameters which we have to select for determination by using risk graph. This is PA, PB, and these are the demand rates. And then for the commercial point of view, we have to select the consequences, then PA, PB, possibility of avoiding the hazard factors, and then the demand rate. So here the exposure or the exposure is not here, because exposure is in the case of personal safety only, that how many hours operator is available in that area. For the commercial or for the environment, it is not our parameter to be selected. So this is a difference in commercial risk graph and safety risk graph. So here it is also giving the example that for the consequence, if you are selecting CA, for example, if it is a compressor damage, the consequence is compressor damage, and the compressor is between more than 500K to up to $5 million, then we have to select CB based on this. So this is the sample. This is the sample, or we can say the example values. It can be adjusted with respect to company's risk matrix. So in our software, we can determine the SIL level of the commercial graph as well. So each will have its own SIL level, and the highest one will be the SIL level considered for that whole loop. For example, for safety graph, it is coming as 1. For environmental graph, it is coming as 1. But for the commercial, it is coming as 2. Then we can say that the target SIL for this loop is SIL2, because commercial is the driving one, which is driving the SIL to SIL2. So let us try one example by using VAIL-PHA. VAIL-PHA SIL. So let us start from the this information. We can put this information in the personal module or personal tab, and then we can add the summaries in this tab, and then we can add the sessions as well. We can add the attendance of the persons, and then this is the risk matrix I was talking about. We have to select 2 parameters. For example, we are selecting D. This can be added in the with respect to company's risk matrix. For example, D means fatalities, between 1 to 10 fatalities, and probability is between this to this times per year. So risk level is medium, and SIL level is 2. For example, if we are changing the severity and we are changing the this probability, So it can change the SIL level. So for example, 3. And then similarly, depending upon these two parameters, we can calculate our SIL level. So this is this matrix. These two parameters will come from input will become from the HAZOP study, the severity level and the probability, or the team input as well, which is performing SIL determination. And then, for example, this is the example for the risk matrix. And here, let's suppose we have selected CB. I'm talking about safety risk graph. So there is another exposure parameter as well. 4 parameters we have to select. Serious consequence and possibility is almost impossible. Exposure is frequent to permanent exposure in the hazardous zone for the operator. And demand rate is once in less than 1 year. So here we are utilizing the same graph. For example, CB we have selected, and then we have selected FB, and then we have selected PB, and then for the demand rate we have selected W3. So this one, so it is SIL3. Similarly, if I edit it and the team member is saying that no, the consequence is not serious, it is moderate, SIL level will change. Similarly, if a team member is saying that no, it is important, the probability is we have enough number of safeguards, but the frequency of operator is more, it will be SIL3. And if we change the demand rate, for example, once in less than 1 year means relatively high. For example, we are selecting W2, which is 1 in 1 to 10 years, SIL level will reduce. If we reduce the consequence, SIL level will reduce. If we increase the number of protections, SIL level will reduce. So in this way, by selecting these 4 parameters, we can determine the SIL level for safety graph. For example, similarly for the commercial, there are 3 parameters. For example, we are saying that it will cause a minor effect, and the demand rate is also between 1 to 10 years, and we have enough number of safeguards, so no special requirement for SIL level, or we can say 0 or A. Or similarly, if we increase the severity of that consequence, SIL level will increase. If we increase the demand rate, SIL level will increase. So if we reduce the number of protections, SIL level will increase. So this is these are the parameters which we have to select for determining the SIL level by risk graph technique. The next technique is LOPA, layer of protection analysis. Here we are selecting these parameters, and it depends upon the team members only. But in LOPA, there are certain values in the standards which we have to apply. So let us go to the LOPA methodology now. So before going to the LOPA, let us discuss the required documentation for SIL determination. What documents we require, what minimum documentations we require to perform a SIL determination exercise. We need PNIDs, we need cause and effects, we need HAZOP worksheets. So these are the necessary documents. Now the question is, why we need PNIDs? We need PNIDs to identify the SIFs. So we can identify our SIFs in the PNIDs that this is a high pressure, PT pressure transmitter. It is performing the SIL function, and it is closing the inlet ESD valve in case of overpressurization. And this is the BPCS, it is controlling this valve. So with the help of PNIDs, we can determine, or we can identify the SIF loop with the help of PNIDs. Now, why we need cause and effect? How we will know that in case of high pressure, this valve will be closed? We will know with the help of cause and effect that to confirm the final action, we need cause and effect, that in case of high pressure, for example, high level, in this case, it will close these valves and stop these pumps. And in case of this high pressure, it will stop this pump. So this is an example sample cause and effect. So we need cause and effect to, number one, enlisting the SIFs. Number two, confirm the final actions. And then why we need HAZO? Why we need HAZO worksheets for the SIL study, for the SIL assessment or SIL determination of a SIF? Because we need certain inputs for the layer of protection analysis. We need causes from the HAZO, we need consequences, we need severities, and we need number of safeguards which are mentioned in the HAZO. And then out of these information, we will perform our LOPA exercise. This cause will be our initiating event in SIL. For example, this is a human error. This is a sample HAZO worksheet. This is a human error, inadvertent closure of the manual valve on SIL flushing line. So human error, it has certain initiating event frequency, occurrence per year. So in standards, there are different values. For example, if a human error, if a task performed less than once per month, it has separate value, different value. If the task performed more than once per month, in which there is a chance of a human error, it has separate value. So we will go through those values as well. It is available in the company's standards or different data books, reliability books as well, or CCPS handbook as well. And the consequence, we need consequence to calculate or determine the target value. For example, each severity will have target value, target mitigated event likelihood. Basically, it is the total value for which we can tolerate. For example, against 4. For example, severity 4 means single worker fatality. And that TMEL, the value is 10 raised to the power minus 4. What does this mean? 10 raised to the power minus 4 means we can tolerate one fatality in 1000 or 10,000 years. 10 raised to the power minus 4, 10,000 years. So we can tolerate one fatality in 10,000 years. We cannot tolerate one fatality in 1,000 years. So target is our, TMEL is our target or tolerable limit, which we can tolerate. So in terms of production loss, about this much of production loss we can tolerate, and this is our target. So we have to target based on these frequencies. So I will also explain this in the steps of LOPA methodology when we will discuss the LOPA. And then current safeguards, that how many safeguards are there to protect that and that scenario. So all the safeguards which are listed in HAZO, we cannot credit them in LOPA. So there are certain rules which we have to follow, and there are certain limitations. For example, if the alarm is not independent then of the initiating event or a SIF, for example, alarm is on the same transmitter in which our SIF is present, then we cannot take the credit of that. The second thing, we have to check that whether operator will have enough process safety time to take the necessary action. If he have, then we have to take the credit. Number third, if the alarm is prioritized, for example, in control room, there will be number of alarms. So out of those number of alarms, how he will identify that critical alarm? So if the priority is high, then we can only credit that alarm. Similarly, for example, if the cause is failure of a control loop, then we cannot take a credit of control loop as a layer because it is a cause. So we will discuss this in the upcoming slides. So we need this input from HAZO, causes or the initiating events, consequences, and the severities and current safeguard. So this information we required from HAZO. So that's why we need HAZO worksheets for SIL determination. So let us start. What is LOPA? LOPA stands for Layer of Protection Analysis. LOPA is a process to evaluate risk with explicit risk tolerance for specific consequences. So methodology is simple. So let me explain here first. First of all, we have to identify a SIF. After the identification, we have to set the target value. How we can set the target value? With the help of consequence severities. So once we set the target value, we know the cause from HAZOP. We have to give the initiating event frequency and then number of safeguards. All these number of safeguards will multiply with each other, giving certain value. So let me explain the next step. It will be better if I go to the next step. So LOPA can be used at any point in the life cycle of a project or a process, but it is most effective when implemented during front-end loading, when process flow diagrams are completed and the P&IDs are under development. For the existing processes, LOPA should be used during or after the HAZOP review or revalidation. LOPA determines the safety integrity level that should be assigned to a safety instrumented function through calculating the risk reduction provided by the IPLs against a hazardous scenario. So now let us go through the stepwise methodology of LOPA. So the step one is identification of a SIF. We cannot perform LOPA analysis without identification of a SIF. Although also there are two scenarios in which we can apply LOPA method. One is to determine the SIF of to determine the SIL level of a safety instrumented function. Number two, if we want to know that our layers of protection are enough and they are meeting our tolerable limit, we can also apply LOPA. Now we are discussing LOPA analysis to determine the target SIL of a SIF. So for that we need to we need some SIF. So step one is identification of a SIF. So LOPA starts by selecting the SIF from P&IDs and cause and effect charts. LOPA team should understand the SIF description and the consequence of the hazard it prevents or mitigates. Then based on that consequence, there are certain severities in the HAZOP. So for example, this is the generic TMEL values. For the consequence severity 4, the TMEL value is 10 raised to the power minus 4. In HAZOP, the overall severity for that initiating event was 4. Okay, and then based on that consequence severity, we have assigned a TMEL. This is a generic TMEL values. It can be changed with according to the company's risk matrix. So target mitigated event likelihood or tolerable limit is 10 raised to the power minus 4. It means that single or serious injury to public or a single worker fatality can be tolerated in 10,000 years. Or for example, minor injury to worker or health effect can be tolerated in 100 years. If in terms of financial, if the loss is between $100K to $1 million, it can be tolerated in 100 years, once in 100 years. If it is more, then it is intolerable. So this is our tolerable range. So after the identification of a SIF, we have to set our target based on the consequence severity. Once the target has been set, we have to move towards the step number 3. So step number 2, TMEL values. Based on the consequence severity, the TMEL for the hazardous scenario shall be established based on the assigned hazard severity from the associated HAZOP, from the HAZOP worksheet. So this is step number 2. Step number 3 is determination of initiating events. Initiating event can be because of human error. It can be because of external event. It can be because of control loop failure, regulatory failure, or a pump equipment damage, pump failure, or valve malfunction. So each initiating event will have its likelihood of failure per year. For example, BPCS, this is a generic table of the initiating event frequencies. BPCS loop failure 0.1, regulator failure 0.1, pump failure 0.1. So this is the initiating event values for the initiating event. So after the target set, we have to identify the initiating events from the HAZOP. For example, in this case, this is the cause human error, and this initiating event will be 0.01 per opportunity. So once the TMEL is determined, the initiating events, the causes in the HAZOP worksheets that could lead to that hazard are to be identified. Then the frequency or probability of occurrence of those events are to be determined. Initiating events can be due to equipment failure, human error, or external events. So this is step number 3. First was identification. Second was based on the consequence severities, we have set the TMEL values. Number 3 was initiating events. If there are more than one initiating events, then we have to analyze all by adding each initiating event with each other. I will explain in the formula how we can add if there are more than one initiating event. Step 4 is identification of the independent protection layers. IPL should then be identified and assign a probability of operating correctly. For example, we have BPCS control loop, independent control loop of the initiating event, or we have the BPCS interlock, or we have captive key lock system. Each will have its own PFDs. For example, we have independent SIF as a safeguard. It will have its own PFD value. SIL 1 will be 0.1, SIL 2 will be 0.01, SIL 3 will be 0.001. For example, we have PSV as a safeguard. Then we have to see whether if it is in clean service, it has its own value. If it is in dirty service, its own value. If we have dual PSVs, it will have its own value. So we will have to take the values from that database or that table. So this is the step number 4. We have identified the SIF, we have set our target value, we have enlist our all initiating events, and we have assigned its value. Then we have identified our independent protection layers from the HAZOP as well, by keeping all in mind that certain criteria which we have to follow for taking all the safeguards to IPL, because all safeguards are not independent protection layers which can be credited in LOPA. So once all this is identified, or we can calculate the intermediate event likelihood by this formula. IEF, it is the initiating event frequency. Our third step. For example, human error. For example, control loop failure, 0.1, multiply by probability of failure and demand of the first protection layer, multiply by second protection layer, multiply by number of protection layers. For example, we have PSV, we have independent alarm. So their values will be multiplied with each other. For example, we have other mitigative IPL like fire detection, the deluge system, automatic. We can add there as well. For example, if we have some conditional modifier, for example, time and risk factor, occupancy factor, we can multiply that in this formula as well. So this is our step number 5. So this is the intermediate event likelihood. These are the initiating event frequencies, or the initiating events or the causes, and these are the PFDs for the layer 1, layer 2 up to n number of layers, and these are the mitigative IPLs. So before going forward, if there are more than 2 causes, then this is for IEL1. Similarly, for the second initiating event, we have to calculate similar way, and in the end we will add both IEL1 and IEL2. So both initiating events will be added. So once we calculate that total mitigated frequency, we can calculate the PFD. How we can calculate the PFD? By this formula. We have assigned our target as a second step, the tolerable limit divided by our calculated value, which was the multiplication of initiating event frequency and probability of failure on demand of number of protection layers. So TMEL divided by total mitigated frequency, we will have PFD. Once we calculate the PFD, we can calculate the RRF with this expression. RRF is equal to 1 over PFD. And then in the table which we have shown in the earlier, from that table, we can calculate the SIL level. For example, the RRF is coming between 100 to 1000. 100 to 1000. It means that it is SIL 2. If it is coming between 1000 to 10,000, it will be SIL 3. If it is 10 to 100, SIL 1. If it is less than 10, it will be SIL 0. So through this, we can calculate or assign a target SIL with the help of layer of protection analysis method, LOPA method. So let us try one example. For example, this is a generic high pressure SIF of a reactor, and let me go to the LOPA analysis. Here, the initiating event is loss of reaction in reactor leading to high pressure in the reactor. Because of loss of reaction, there is a high pressure in the reactor. This is a cause. Before going to that, let me go to the Tmal values. First of all, we have identified the SIF. Then based on the consequence, we have assigned the target values. For example, for safety, we have assigned the target value severity 5. Severity 5 means disasters, and it means that Tmal value 5. We can edit our values, for example, for safety, for environmental, for commercial, for reputation. We can edit the values of Tmal here according to the company's risk matrix. So, for example, say severity 5 for the safety. Severity 5 means there will be a disastrous impact and there will be a multiple fatalities. So the Tmal target mitigated frequency is 10 raised to the power minus 5. And for the environmental, it will be a slight effect 0.1. These are the generic severities we have selected to show you different results. Okay, now target has been set. Now coming towards the third step, which is the identification of the initiating event. So from the HAZOP, we have identified that there are two causes. One is loss of reaction in the reactor leading to the high pressure in the reactor. The second one is the malfunction of the control loop, which is causing the control valve stuck to open position. So we will analyze cause by cause. The first cause is loss of reaction. In that scenario, in HAZOP, there are three protections. There are three IPLs that we have seen in the HAZOP. For example, the first IPL is BPCS, Basic Process Control Loop. That PAC is available and it will regulate the pressure by throttling of the valves. Okay, we can credit it 0.1. 0.1 value we are taking from the standard. Then alarm with operator response. PT01, pressure transmitter is available with high pressure alarm. We are not crediting this. One means we are not crediting because these values will multiply with each other, and one means it will not make any impact. So why we are not taking a credit? For example, the transmitter for the basic process control loop and this alarm is same. So if we want to take the credit of the alarm, it should be independent. In this case, it is not independent. It is the part of a same loop which we are taking credit as a BPCS. So that's why we are not taking a credit of alarm. And then in case of high pressure, we have a PSV on the reactors. So it is a clean service. So we are taking 0.01. So there are different values in the table. For example, if it is a dirty service, we can choose 0.1. So based on this. So now as per the formula, initiating event frequency multiply by PFD layer 1, multiply by PFD layer 2, multiply by PFD layer 3. So all these four values will multiply with each other. If we will have any mitigation layer, it will also multiply. If we are using any conditional modifier like time at risk factor, occupancy factor, ignition probability or explosion probability in case of fire, so it will also multiply with these values. So now 0.01 multiply by 0.1 multiply by 0.1, we have 0.0001. It is the IEL, intermediate event likelihood, the formula what we have seen in the presentation. Now this is for the first initiating event. If we have more than one, then we have to consider that as well. For example, the second cause is malfunction of PIC control valve. Now it is a BPCS failure. From the last case, first cause, we have taken this BPCS as a credit in the protection layer. Now, if this is the cause, then what will happen? We don't have any other BPCS. One, we have alarm, but it is a part of that loop which is causing a problem. So we cannot take a credit of this in this case as well. And then PSV, same PSV which we have taken credit in the previous case. So in this case, we have less number of protections. So this is a driving case. We have less number of protections. This is a driving case. Initiating IEL for the first one plus IEL for the second one. First one was 0.0001, second is 0.001. It will be added. We will have total mitigated frequency 0.0011. Now from the formula, we can calculate the PFD. How we can calculate the PFD? By dividing TML value. This is a numeric value. This is also a numeric value. We can calculate the PFD value by dividing TML with total mitigated frequency. 10 raised to the power minus 5 divided by 0.0011. We will get this value 0.009099. Similarly, environmental. It have different TML value. Result will be different. Commercial have different TML value. Different severity. Result will be different. Reputation have different TML value. Result will be different. So for the safety, the TML or the severity was highest. SIL is 2. Although environmental, commercial, reputation have less SIL level, but we can say that for this whole loop, this PHH will have the target SIL, SIL 2, because highest one will be the target SIL. Let's suppose the team members are saying that no, it is, or the HAZOP is saying that no, the severity is not that much high severity. Then we can reduce the severity to 4. It will impact our SIL level. Our SIL level will be reduced. It will be SIL 1. Now commercial and severity both have same severities. So SIL level is same. So in this way, we can determine the SIL level by using layer of protection analysis method. So these are the steps I am repeating. First of all, we have to identify, then we have to assign the target value, then initiating event value and its frequency, then number of IPLs we have and their values, we have to multiply them with each other. We will have a total mitigated frequency. For the calculation of PFD, we have to divide TMEL with total mitigated frequency. We will have PFD. RRF we can calculate by dividing 1 over PFD, we will get RRF. Then we will look up at that table. If the RRF is between 10 to 100, it will be SIL 1. If it is less than 10, it will be SIL 0. Less than 10, it will be SIL 0. If it is more than 100, let's suppose if it is more than 100, then SIL 2. So if it is between 100 to 1000, it will be SIL 2. If more than 1000, it will be SIL 3. So in this way, we can calculate the target SIL with the help of layer of protection analysis method. Moving forward, now we have determined our target SIL by using 3 methodologies: risk matrix, risk graph, and LOPA method. So in our software, we can also calculate the test intervals, that after how many interval, after how many frequency we can calculate, we can test our SIFs, functional test, how we can, when we can perform the functional test of our SIFs. So we can calculate that test intervals in our software as well. So it is considered to be a major parameter in SIL verification phase. SIF test interval signifies the interval at which periodic proof tests are conducted. It indicates how strong this requirement is, as during the SIL verification, the proof test interval may be adjusted to accomplish the target SIL. So we have calculated the PFD of that particular sensor or loop, if it is 1 out of 1. With the help of this formula, we can calculate the testing interval. Then testing interval will be equal to PFD multiplied by 2 divided by failure rate, undetected failure rate. So from this formula, we can calculate the testing interval. Now, We can also perform SIL verification, whether with the help of reliability data, we are achieving our target SIL. We are meeting our target SIL or no. So if we are not meeting our target SIL with that particular reliability data, then we have to make some changes. We have to make some changes in the test intervals. We have to make some changes in the architectural voting or the reliability data itself. We have to replace that equipment with the much better reliability data, lower failure rate data. So SIL verification is carried out to calculate the actual SIL level or PFD of a SIF loop to know if the risk reduction required is achieving depending upon the following factors: architectural voting, testing intervals, reliability data. So with the help of verification, we will check that whether the achieved SIL is meeting the target SIL or no. This is the formula, same formula which we have seen in the test interval calculation. So each formula is different with respect to its voting. For example, if the voting of the transmitter pressure transmitter is 2 out of 3, then for the actual SIL calculation, we have to utilize this PFD formula. Lambda du, undetected failure rate of that pressure transmitter, square into test interval square. Test interval, we have to put some value, for example, the shutdown frequency of the plant. We will check at the shutdown frequency whether it is meeting the target SIL or no. If it is not meeting the target SIL, then we have to reduce the test interval up to that level in which it will meet the target SIL. If still, for example, if it is still not meeting at 6 months and 6 months interval is not possible for the running plant, then how we can test that loop? Then we have to change some hardware changes, like we have to add some protection layer so that our target SIL will be reduced. We have to change the equipment to improve the failure rate with the to change the equipment with the improved failure rate, or we have to change the architectural voting. So by this we can ensure that we have to meet our target SIL. So SIL verification is carried out by using simplified equations method as well. There are different methods of SIL verification. We can verify the SIL by Markov analysis, by simplified equations as well. So this is the example of simplified equations. Software is designed and developed as per ISA TR 840002 to carry out SIL verification. We can also perform spurious strip rate calculation by these formulas as well. These are the safe failures. For the PFD calculations, these are the undetected failures. For the spurious strip calculations, these are the safe failures, safe failure rates. So architectural voting to be taken from PNIDs and cause and effects. For example, if it is 1 out of 1, 1 out of 2, 2 out of 3. The reliability data to be taken from Exida or Orida, or if it is maintained by the company. Testing intervals are adjusted to make actual SIL level equal or greater than the required or target SIL level. Then we can also perform spurious strip rate calculation, and we can also develop safety requirement specification as well. Spurious strip rate is also calculated for all the components of the SIFs, initiators, logic solvers, and final elements. And then spurious stripping is the unwanted tripping of the system caused by any of its elements when no in demand. So we can calculate the unwanted trips calculation as well. This is the SRS, safety requirement specifications for specific SIF. In our case, high pressure SIF, all the information related to SIF tag number, equipment tag number, and then the description, target SIL, SIF initiating devices, initiating voting, what is the voting, and then all this information will be in this safety requirement specifications. What is the demand rate, what is the proof test intervals, mode of operation, manual shutdown requirement, bypass override requirements, what is the process safety time, what is the all this information will be covered in SRS sheets. So this data can be maintained in our software as well. And then we can also calculate MTBF, MTTR in this VAIL-PHA SIL module. Mean time to repair refers to the amount of time required to repair a system and restore it to full functionality. MTTR clock starts ticking when the repairs start, and it goes on until operations are restored. This includes repair time, testing period, and return to the normal operation condition as well. So to calculate the MTTR, we have to divide the total maintenance time by the total number of maintenance actions over a given period of time. So we can calculate the MTBF, we can calculate the MTTR, we can also calculate the failure rates as well. For example, in initiator, we have performing the test 14 times, and out of 14 times, number of failures are 3. So this will be our actual PFD that can be used in the SIL verification. So in this software, we can calculate that as well. So mean time between failure is the predicted elapsed time between inherent failures of a mechanical or electronic system during normal system operation. MTBF measures the predicted time that passes between one previous failures of a mechanical or electrical system to the next failure during normal operation. In simpler terms, MTBF helps you predict how long an asset can run before the next unplanned breakdown happens. So both MTBF and MTTR can be calculated in this SIL module of VAIL-PHA. Then we can also generate number of reports. VAIL-PHA offers a number of options to generate various type of reports in Excel file as well as PDF form as well. We can generate risk matrix report, risk graph report, LOPA report, comparison summary sheet. For example, if we want to check that by utilizing risk matrix approach, what is the SIL level, by risk graph approach, what is the SIL level, by LOPA, what is the SIL level. So we can make a summary as well. And then the test interval report as well as the SIL verification report, SIL verification summary sheet. We can also generate, STR reports and SRS reports as well. Now let us go to the case study where we have performed SIL studies for a number of clients. We are not showing the name of the company for which we have taken the case study of, and to respect the confidentiality agreement with our client. So we have performed number of SIL studies across the world. This is one sample case study. The objective of that was identification of a gap between existing SIF or SIFs and IEC 61511 or client guidelines requirements to maintain or reduce the corporate risk, development and implementation of lifecycle program for all the existing and new SIFs, SIL classification, verification, testing calculation, interval calculation, and preparation of SRS and STR reports as well. Then subsequently, we have to suggest them the test plans to maintain the SIL at desired level. So this was the objective of the project, and this was the scope. We have to carry out the following activities. We have to prepare a master plan, how we will execute these activities. Then we have to perform the SIL assessment or SIL determination or SIL classification. And then we have to verify whether those classified SIFs are meeting or no, based on the reliability data. And then calculation of testing intervals, preparation of testing plans, and then preparation of safety requirement specifications, and then preparation of safety lifecycle management system. So this was the number of SIFs which we have classified, or we have determined the target SIL. For example, there are a number of plants. Each plant have had separate number of units, and these are the number of independent instrumented protection functions. So total SIFs were 2,324, which we have classified as a part of a study. So main deliverables of that project was master plan for safety lifecycle management, list of all the SIFs with the assigned SIL, SIL assessment report, testing interval report, SIL verification report with calculation sheets for each SIF, independent sheets, SRS and spurious strip reports, gap analysis report and recommendations for each SIF. And then we have to deliver our software as well, so that in future if they have to calculate their own SIL level, they can calculate as well. So these were the stages to execute the project activities. In stage 1, we have prepared the master plan. In stage 2, we have carried out the SIL review or SIL classification. In stage 3, we have verified the SIL level And then stage 4, we have developed the test intervals for all those into safety instrumented functions. And then as a part of stage 5, we have developed the reports and recommendations, all the recommendation in which the achieved SIL was not meeting the target SILs. So SIL assessment has been done to estimate the minimum risk reduction required against intolerable risk to bring it to the tolerable region. This risk reduction has been evaluated in terms of SIL level. So these are the results of our study. We are not mentioning the names of the client or the plant to maintain our agreement. So risk graph and LOPA method has been used to classify the SIFs throughout our client facilities. So we have assigned or we have assessed the SIL assessment for 2,324 SIFs, and all this study was carried out by using VAIL-PHA SIL. So total number of SIFs, we have classified SIL 0 as 558 SIFs, SIL 1 1311, and 455 SIFs were classified as SIL 2. There was no any SIF classified as SIL 3 or SIL 4. Then we have gave certain recommendations. For example, all the operating units of the client facility has been undertaken during SIL study. Most of the SIFs meet IEC 61508, 61511 requirements, but there are some SIFs which do not meet the requirements as well. Recommendations have been provided against all SIFs which are not meeting the requirements. Recommendations have been provided, for example, to keep the flame scanners in operation during normal operation, as well as in addition to their use only during startup activity. Spurious trip rate has also been checked, and where it was higher than the target value, recommendations has been provided. Redundancy check of all the components of a SIF have been performed, and wherever there is a gap have been highlighted to client's team. And there are certain storage tanks on which only low level SIFs are present. On contrary, similar type of tanks have high SIFs as well. Both low and high SIFs should be available. So this was one of the recommendation. Some PNIDs that are not updated needs to be updated. Hazard reports that are not either available, not updated, should be updated. Implementation of these recommendations will reduce the risk level to corporate tolerable level or alert level. So these are the our sample recommendations. So these are the sample classification report, SIL classification report. So this is the table of content, introduction, background, objective of the scope, report structure, SIL assessment review session, the study basis software we have used, assumption study we have made, findings and results, recommendations, calculations, and these are the appendices which we are making a part as a report: SIL classification methodology, summary sheet, risk graph worksheets, LOPA worksheets, validation sessions, minutes of meetings, and attendance sheet as well. So this is the sample SIL verification report, and this is the sample SRS or STR report, and this is the sample lifecycle document, lifecycle management document. It was also a part of our deliverable. It contains purpose, scope, advantages of safety lifecycle, abbreviations and definitions, phases of safety lifecycles, safety lifecycle requirements, hazard and risk analysis, allocation of safety functions to protection layers, SIS safety requirement specifications, SIS installation and commissioning phase, validation phase, operation and maintenance phase, modification phase, decommissioning phase, verification phase, and then functional safety assessment, and then requirements of application software, including selection criteria for utility softwares. All these was the content of this safety lifecycle document, which we have prepared as a part of our deliverable. So with this, we have completed our webinar. So now we can take questions.
Okay, one question from Mr. Waqas Ahmad. Is there any specific qualification or certification required for the maintenance team, or any competent engineer / technician can work on SIL certified plants?
Yes, there's no certification required for the technicians and for engineers working in the plant. Yes, for execution of SIL classification, SIL verification exercises or studies, it's better the persons are trained or certified, whatever is the company preference. But basic knowledge is required about IEC 61511, 61508, and ISA standards, so as information can be used in a proper way.
Next question. How to do test for SIF initiator, logic solver, and final element and send to Exida for certification?
See, there's no third-party certification, like if any SIF has to be tested. The SIFs are installed at the plant. There's not one SIF, there's a complete ESD system and ESD loops. And these SIFs can be tested during startup, shutdown. In between, their testing is difficult, right? And there's a partial stroke principles or mechanisms are available to execute this SIF testing during plant operations as well, but is a partial testing if you have all the safety mechanisms in place. So there's no practically certification program for the SIFs. Yes, the manufacturers are getting third-party certifications for their hardware, and they may come to Velosi or maybe Exida or DNV if they want to get certified, but they need to prove the records and failure data to demonstrate that like their hardware, whether initiator, logic solver, or final element would be able to meet applicable required SIL reliability criteria.
Next question. When we do SIL determination, how do we know which methodology, risk matrix, risk graph, and LOPA, we have to choose? Any criteria for choosing methodology?
See, these are the company's preferred mechanism, preferred methodology. There are three major techniques are there for SIL classification: risk matrix, risk graph, and LOPA. First two are the qualitative, merely they depend upon the selection by the user, whereas LOPA is semi-quantitative, where the data is there and failure frequencies and then multiple divisions are there, which are more like a semi-quantitative approach, I would say. So it's a company preference, which technique you wish to use.
Next question. We have one PSV on a pressurized vessel. Can we use PHA SIF as IPL to remove PSV for a few hours and install it after recalibration?
No, these PSVs are one of the important high pressure protection carrier, and these PSVs are installed in accordance with ASME Section 8, Division 1 and Division 2 requirements. These PSVs, if there's one PSV, cannot be removed from the system, because at that stage, if there is any abnormal scenario, then system cannot be protected. So in general scenario, you have to have two PSVs if you wish to take one PSV off during normal plant operation with proper positive isolation valves installed.
Okay, next question. Why plant design life is not considered while selecting Tmal value?
No, the plant life is there. Plant life is 25 years, 40 years, 50, 60. Plant lives are extended. TMEL is a target, what could be the impact of the hazard on the plant itself in terms of asset integrity, or on the people, or on the environment. So if the loss would be bigger, it means you would require more reliable SIFs which can protect the system. If the loss is lesser, then less reliable system can provide the required protection. So it's not related to life of the plant, it is related to like a subsequent severity or basically effect on the plant, people, or environment.
Next question. You said risk graph and LOPA were used to determine SIL. Why can't we use only LOPA or risk?
A combination, like LOPA require more efforts, risk graph require less efforts. So people try to use risk graph for all SIFs, and for SIL 2 and above, they try to go LOPA. But if you ask Velosi what should be preferred solution, we would normally recommend to go by LOPA. LOPA is more detailed working and more reliable as compared to risk graph or risk matrix.
Okay. Next question. Which one of the risk assessment methods, risk matrix and risk graph, is efficient in identifying and mitigating the risk? Also, which standard is used to define the severity and probability scores in risk matrix method?
See, risk, the level is risk matrix is more qualitative, and risk graph takes a little more sophisticated information, more better, and LOPA is more detailed one and require more information. So that is also the kind of effort you would be putting in, so you would be getting the better result. Secondly, when we are selecting this, there are companies' own risk matrices or risk management procedures, which are basically complied while doing SIL studies. Like if you take ADNOC, so they got SIL standard, they got HAZOP standard, and both of these standards are applied at their stages, and then SIL assessment is done. So if somebody is not having, so they can go to straight away to IEC 61511 or ADNOC or the BP or Shell or Exxon or Saudi Aramco. All these companies are having their own basically SIL procedures or risk matrices which can be used.
Okay. Next question from Mr. Swapnil. I am working on gas processing plant GPP. Our FNG detection system is initiating ESD on fire detection, which in turn automatically initiates ESD plant shutdown. In this case, the FNG SIS to be considered for SIL classification, we have already considered SIL2 for the FNG ESD. However, client is asking for SIL3 ESD. Is it required to have SIL3 on FNG system ESD?
See, this is a very complicated situation. The issue is if ESD system is linked with fire and gas detection system, the probability of unwanted shutdown due to spurious trips can go high, and it will depend like if the fire and gas detection system is properly designed, the fire zoning is properly identified, and the voting system which would initiate the shutdown is properly established in studies. So if, for example, if somebody says 2 detectors out of n can initiate shutdown, so in the facility, 2 detectors can be giving false or spurious signal anytime, and it will cause the trip. However, if you see in a specific fire zone, if there's a gas detector, there is a heat detector, or there is a toxic gas detectors, if all 3 of them are giving some abnormal situation, and if that caused the shutdown, that is acceptable. So it has to be seen how your fire and gas detection system is designed and what level of controls are in place. Otherwise, you will have a lot of spurious trips or unwanted shutdowns. Now, coming back to normal, fire and gas, general acceptable SIL level is 2. For 3, it would be very difficult to achieve because when you will be testing any number of, let's say, oxidation type of detectors or infrared type of detectors or heat detectors, normally their failure rate is 1 out of 100. And if you want to go to level 3, you should go to 1 out of 1,000. And you may not be able to maintain that SIL level.
Next question. Is machine monitoring sensor needs SIL assessment or verification requirement?
See, SIPs, if they are related to high vibration rated trips, and those sensors are required to be SIL rated, yes.
And the following after that, whether we should rely on target SIL defined by compressor manufacturer or BN system.
See, manufacturer normally they try to say, okay, my SIF or my transmitter or my logic solver or my final element would meet SIL level 3 criteria. It's responsibility of buyer to ensure that they are not being defeated. Remember, we have seen in Pakistan, they're selling bed mattresses and saying, elephant child can sit on the mattress and it will be sustained for next 25 years. But if you, after 1 year or 2, you go back, oh, it's already damaged. So they would say, oh, maybe there's some water or some urine went by the child and that's why it caused this damage. So there's exception. And with that exception, their warranty is gone. So we don't know what kind of exception the manufacturer or vendor are putting for the SIPs or hardware. So it has to be ensured that you have a proper reliable supply, and you before you buy any hardware for a SIP, you should check the prevailing industry if the same hardware is working reliably in the neighboring industry of the same kind.
Okay, last question. If SIL2 be retained for FNG system ESD. Then how to calculate the PFD for FNG detection system ESD. How we can make sure that the PFD will be 1 out of 1,000 year and not 1 out of 100 year.
See, this will depend upon the hardware, what you have selected, who is the manufacturer of your fire and gas detection system, how your fire and gas detection system is being managed, starting from the detector to wire to the fire and gas like a console, how you are making it. So it is a combination of everything. It's not like a shortcut. Right. Thank you very much, everyone. And I hope this presentation was useful. And if you need any further assistance, questions, don't hesitate to contact us through our webpage and we will try to reply you. Thank you.